In this lecture video, we'll be constructing confidence intervals to estimate population means when the population standard deviation is a known value. When estimating a population mean, the best point estimate is a sample mean. So we'll center our confidence interval on the sample mean, and the width of the confidence interval will be determined by our margin of error. And inside this range of values is where we believe the population mean is. When the population standard deviation is known, we will use it in the calculation of our margin of error. We will also be able to use the z-distribution and calculate our z sub alpha over 2 values when finding our margin of error. We will also be able to use our calculators to construct these confidence intervals. The calculator function that we will need is z-interval. Let's review some notation that we're going to need when constructing these confidence intervals. Mu is the population mean, while x bar is the sample mean. Capital E is our margin of error. Lowercase n is the sample size. And sigma is the population standard deviation. We do have 3 requirements when constructing this type of confidence interval. It must be that the sample is a simple random sample, the standard deviation for the population is a known value, and the data needs to either be normally distributed or the sample size needs to be greater than 30. When we're calculating the confidence interval limits, it's important that we round to the correct number of decimal places. This is called the round-off rule. If we are given an original set of data, we need to round the confidence interval limits to one more decimal place than what is used in that original set of data. If we are instead given summary statistics for that data set, we will round our confidence interval limits to the same number of decimal places that are used for the sample mean. Let's get started with an example. In this example, we are told that some randomly selected statistics students participated in an experiment to test their ability to determine when 60 seconds had passed. 40 students yielded a sample mean of 58.3 seconds. Assume that the population standard deviation is known to be 9.5 seconds. What is the best point estimate for the mean time of all statistics students? That is, what is the best point estimate for the population mean? The best point estimate is the sample mean, and in this case, that is 58.3 seconds. Now, let's construct a 95% confidence interval estimate for the population mean for all statistics students. Let's do a quick check of the requirements to make sure that we can do this type of confidence interval. The first requirement is that it's a simple random sample. We are told that the students are randomly selected. Second, it must be that the population standard deviation is a known value. We are given this population standard deviation of 9.5 seconds. Third, we need the data to be normally distributed or the sample to be greater than 30. Here we have 40 students, so we meet all 3 requirements. Now let's construct our confidence interval. Let's list out everything we know. We have a sample mean of 58.3, a sample size of 40, a population standard deviation of 9.5, a confidence level of 0.95, which leaves 0.05 left over for alpha, and dividing that by 2, we have 0.025 for alpha over 2. We'll first calculate the confidence interval by hand using the formula for the margin of error, and then we'll use our calculators. In order to calculate our margin of error, we are going to need z sub alpha over 2 for this situation. With a confidence level of 0.95 in the center of our normal distribution, z sub alpha over 2 is the value that separates the alpha over 2 portion, or 0.025, in the right tail. Using the z-table or INV norm function, we find this z value to be 1.96. So we have that E is equal to z sub alpha over 2, 1.96, times sigma, 9.5, divided by the square root of n, the square root of 40. Putting this into our calculators, we find that E is equal to 2.9. Notice that I rounded to the same number of decimal places as given for the sample mean. This is a situation where we are given summary statistics, not the original data values, so we will round to the same number of decimal places as given with the sample mean. In this case, that's 1 decimal place. Now we can calculate our confidence interval by taking the sample mean plus or minus the margin of error. That's 58.3 plus or minus 2.9. This gives us an interval from 55.4 to 61.2. Let's take a look at how to do the same process with a calculator. We need the z-interval function, which can be found in the Stat Tests menu. Z-interval is option 7. Since we are working with summary statistics, we need to first select Stats. Then we can enter our population standard deviation of 9.5, our sample mean of 58.3, our sample size of 40, and our confidence level of 0.95. Pressing enter on calculate gives us the same interval estimate that we just calculated by hand, 55.4 to 61.2. This interval is a 95% confidence interval estimate for the population mean, and we could state our results by saying we are 95% confident that the interval from 55.4 to 61.2 actually does contain the true value of the population mean. Now, based on these results, is it likely that their estimates have a population mean that is reasonably close to 60 seconds? Yes, 60 seconds is within this confidence interval estimate that we created. So it is likely that the mean is reasonably close to 60 seconds. They were reasonably accurate with their ability to determine when 60 seconds had passed. Now let's look at an example when the original data is given to us instead. In this example, we have that 14 different second-year medical students measured the blood pressure of the same person. They obtained these results listed below. Assuming that the population standard deviation is known to be 10, construct a 95% confidence interval estimate of the population mean. As before, let's list out what we know. We have 14 data values, so n is equal to 14. We also know that the population standard deviation is known to be 10, and the confidence level that we are interested in is 95%, or 0.95. Notice that this time we are not given the sample mean. Instead, we are given the sample data values. To calculate this by hand, you could find the sample mean by adding up all 14 values and dividing by 14. But to calculate this using our calculators, we'll start by entering our 14 data values into a list in our calculator. Then, when we go to the z-interval function, we will instead select data rather than stats. We have the original data, not the summary statistics. We'll enter our population standard deviation of 10, and for the list, we'll put in list 1 since that's where we entered our original data set. Our confidence level is 0.95, and when we press calculate, we have our confidence interval estimate for the population mean. We need to round to one more decimal place than what's given in the original data set. Since the original data values were rounded to no decimal places, we will round to 1 decimal place. This gives us a confidence interval of 128.7 to 139.2. To quickly review what we just did, we first entered all of the values into a list. Then we used the z-interval function, and we selected data and put in the correct list. This gave us a confidence interval of 128.7 to 139.2. We are 95% confident that the interval from 128.7 to 139.2 contains the actual mean value, or in this case, the blood pressure of this person. That concludes this lecture video on how to construct a confidence interval to estimate a population mean when the standard deviation is known.